Herman for organizing this, with Irene doing all of the interactions with the problematic visitors who didn't understand instructions and other things. But it's a lovely place, and I'm happy to be here. What I was asked to do was to give a introductory talk on how you make materials. This is going to be really very pedagogical. I'm going to try to teach you how you can grow materials. For today, tomorrow I'm going to try to give a rather strange talk. I'm going to try to explain where do ideas come from, which certainly, since we're talking about the younger people, and I assume younger means anyone younger than me, so it's an important question, because we often see presentations of results and brilliant things that have been done, but how the heck did you come up with that idea? And this is the key step if you're trying to develop a research project. So that'll be for tomorrow. So today I'm going to try to tell you how to make things, and tomorrow how to come up with ideas for making things. So I come from Iowa State University, which is 160 years old, a land-grant university in the middle of the United States. People ask me, where's Iowa? It's next to Chicago. That's sort of how people figure out where it is. Ames Lab is a slightly newer construct. This is also on the campus. It's one of the original Manhattan Project laboratories. Soon after the Manhattan Project, it became a basic science lab, and for the past 70 years, it's really focused on the physics, chemistry, metallurgy of novel materials. Okay? My own group within this setting looks at a wide variety of states and transitions in metals, generally in metals, ranging from superconductivity, which is the focus of this project, down through metal insulator transitions. We try to find new ferromagnets, quantum critical materials, spin glasses, quasicrystals. We generally do this by trying to design, discover, and develop systems that let us ask sharp questions and hopefully get clear answers. Okay? So if anything I cover here is of interest, we have a web page maintained by my colleague Sergei Budko that has all of our articles, review papers, scurrilous suggestions, recipes, jokes. You can find it. All right, so we're going to start, and sort of with any topic like this, we should start with a story. Okay? So by the end of the lecture, I want you to know where crystals come from. Okay? And many physicists have sort of a poor idea of where samples, materials come from. So let's have an example of this. So, a story. Once upon a time, there was a single crystal. And there was an excited student who was going to mount it onto, the diffractometer or whatever. And the student dropped it. And it broke. Okay? There was great anger in the land. Okay? The person who grew it, my dear friend David Mandera, said, do you have any idea where single crystals come from? Because the student didn't seem to be so bothered by this. Okay? And the student said, yes, I know where single crystals come from. They come from FedEx. Okay? So this is the answer I want you not to give. I want you to know the proper reply. Where do samples come from? Okay? So, if we want to talk about materials, okay, as physicists, we're going to have to talk about a phase space, okay? Now, we're familiar with many phase spaces, but unfortunately, many scientists, many physicists, maybe even many condensed matter physicists are less familiar with the phase space we're talking about than they should be, because many scientists have a schematic view of the periodic table. Okay? They know there's hydrogen, there's stuff like hydrogen, there's stuff less like hydrogen. There are hard metals, there are semiconductors. I would love to find that in the backyard. The Portuguese took a lot of that from Brazil and put it all in their churches. This stuff might not be real. The students know this is on the final exam, and that's bombs and nasty stuff. And that's how a lot of people look at this. Now, there's an advanced version of this. The advanced version is this hurts your fingers and that changes your voice. Okay. Right. The periodic table is the crowning achievement of chemistry and physics for the last 2 centuries, okay? It's the palette we paint with, it's the puzzle box, it's the ultimate do-it-yourself project. It's what we can create all the known and unknown materials from. Okay? Now, if we want an analogy, I enjoy cooking. Here is a subset of the cuisinal periodic table. We're off on the vegan side of the periodic table now. But just with this subset, we can combine these things in different ratios, in different amounts, and make lots of delicious dishes that we can enjoy. In the same way, if you're familiar with the periodic table, you can mix different elements and come up with completely different materials. We can have a dilute rare earth heavy fermion. We can have magnetic superconductors, just depending on how we mix things, okay? We have roughly 100 elements we can play with, and the number of materials we can look at is immense, okay? So, the aesthetics of what we do really can be, described by analogy either to cooking or to fishing, and I assume we'll post these lectures at some point, Herman, yes? Here are references to essays where I've described the aesthetics as similar to cooking or fishing or jogging, okay? Now, in the same way, there are many different forms you can come with your ingredients, okay? I can do very different things if I have nice pork chops as opposed to ground pork. Okay? In the same way, if you want to study the properties of materials, you can use single crystals or polycrystals, okay? For much of what we do, single crystals have an advantage. So what I want to do is say, why do we want to grow single crystals? And then to the bulk of the talk, how do we grow single crystals? But first, why do we grow single crystals, okay? Well, look, anisotropic properties. I come from an agricultural state. As I was taking the train from Puerto to Braga, I saw that there were lots of cornfields even here. And a cornfield is an anisotropic optical material if it's a single crystalline cornfield. If the farmer plows the field all in one direction, at a certain angle, you can see through it, whereas at other angles, you cannot. Okay? You can appreciate this anisotropy if you have a single crystal. Okay? On the other hand, if the farmer, just for infinite boredom or for some other reason, plows a polycrystalline field or subdivides, then you no longer can appreciate this anisotropy. No matter how you look at this, you don't appreciate that it's optically anisotropic. The same thing happens for single crystals of compounds, not just for optical, it can be electrical, it can be magnetic, it can be any type of anisotropy. You appreciate it more clearly in a single crystal. Okay? Now, in addition, if you have a single crystal, you don't have grain boundaries. Grain boundaries can cause stress and strain. You tend to have higher purity in a single crystal, but not always. So, if we want to understand the intrinsic properties of a material, we want to measure it in a single crystal. Even if we're going to use it in polycrystalline form, to understand it, to master it, we need to understand these properties. Okay? So that's one reason for single crystals. There's a second reason, okay? They're pretty. Now, this is important. As a scientist, this is one of the chances to be close to nature, proximal to an essential force. When you open a crucible and see a beautiful crystal like this, it's a moment of zen. You can appreciate the beauty, the aesthetics, the geometry. And then you can start doing your measurements. But it's nice. When in Madrid, where we set up a growth lab, I remember one of the students, when we had the first crystal, he goes, guapísimo. Right, I made this. It's addictive, it's wonderful. So, a lot of what I'll talk about is summarized in these papers. They are on my webpage. Hopefully you can find the references as well. So, how do you make single crystals? Well, the equipment is modest. This isn't a synchrotron. This isn't a neutron. This isn't a giant castle of physics. This is a simple lab with glorified pizza furnaces, tables of high purity elements. We have about 80% of the elements in high purity form that we use. Complicated cutting devices that you can also liberate bicycles with if you need to fund your research. And, devices for enhanced gravitational decanting. All right, so the spaces are small. There's a delivery room-like atmosphere. Crystal birth, blah, 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 blah. Crystal growth like birth can be messy. On the other hand, it's addictive. It's spontaneous symmetry breaking at its best. Let me show you how we do it. Okay, so first you need an idea. We'll talk about that tomorrow, okay? But now that you have an idea, okay, let's figure out what to do. I want to grow something, okay? In the same way, if I say, I want to go to Slovakia. Why would I want to go to Slovakia? I want to go to Slovakia. I would look at a map to figure out how I get there, okay? In the same way, if I want to grow something, I look at a map. This is the map many of you are used to. This is the map I want to explain how to use. They're the same thing. They tell me where there's liquid and where there's solid and how to get from one to the other. Okay? So we're going to spend a little bit of time talking about phase diagrams because this is the essence, the tool you use for trying to grow materials. Okay? So let's look at this. Axes, temperature, composition. I have silver, pure silver here, pure barium here, and I'm mixing silver and barium as I go across, okay? At the high temperatures, I have a single phase region. I have a homogeneous single phase liquid, okay? This liquid region extends down to different minima. These minima are called eutectics, okay? These define the lowest temperature that I can have a liquid to play around in for that compositional region, okay? If we're interested, as we will be, in growing single crystals out of liquids, it's important to know where the liquids exist. Okay? Now, if you say this is already abstract, okay? It's not. Most people are very familiar with this phase diagram, which is pure water and adding salt. Okay? And the reason I'm pointing this out is, at least in my part of the world, we're going to start having ice on the ground soon. When there's ice on the ground, if it's pure, water freezes at 0 Celsius, but if I throw some salt on it, I can actually lower the melting point and actually have it so that I can still have liquid water and salt down to about minus 20 degrees Celsius. That's because I have a eutectic here in the water-salt phase diagram. So we're used to this in everyday life, at least in colder parts of the world. Okay? Now, if we go back to the sense of wanting to grow materials, here's a beautiful eutectic with gold and silicon. Pure gold, pure silicon. As I add silicon to gold, the melting point drops from 1064 down to 363. This is a sort of swimming pool of liquid that I can try to grow all sorts of interesting gold, silicon, whatever ternary, quaternary materials out of. So eutectics are convenient regions of liquid, and they sort of give me a region I might be able to grow materials from. But let's go back to how do we grow materials, and to do that, let's go back to our phase diagram. Silver, barium. So we have liquid here, we have eutectics. Now we have these lines. These are compounds, okay? Now, there are two types of lines. I'll start with this one, which is a congruently melting material. That means if I have silver to barium, and I heat it up, I heat it up, I heat it up, it's a hot solid, it's hot, and then at 770 it goes from being a single phase solid to a single phase liquid. Okay, so this melts congruently. There are a lot of methods for growing materials that melt congruently. You could just solidify them, usually with some small temperature gradient. Okay? Now, on the other hand, we have this sort of line that separates our single phase liquid from our multi-phase, in many cases, regions. This is called the Liquidus line. Okay? Now, this is important, and we'll come back to it again later. This is the key to crystal growth, okay? But for right now, we can see if we cool down at this composition, okay, we have a single phase liquid until we hit this line, and then this line defines the composition of the existing liquid as I cool down, as I'm starting to grow silver barium. This defines the difference between a single phase region and a two phase region. Here I have a liquid of this composition and a solid of this composition. Okay? So we'll come back to this in greater detail in a moment. I want to start labeling the other parts. Remember, this material melted congruently. I went from a homogeneous solid to a homogeneous liquid. You have these other compounds that as you heat them up, it doesn't melt. It decomposes at this temperature, this paratectic temperature. This compound decomposes into silver 2 barium and a liquid, the liquid composition being defined by this Liquidus line. We can see it perhaps more clearly here. Silver 2 barium 3, we heat it up, it decomposes at 360. We end up with silver barium and a liquid of this composition, and it's only at this temperature I enter into a single phase region. Okay? Now, this is important because if I try to, for example, cool down a silver barium liquid, 50-50, I first would grow silver 2 barium, I would then grow silver barium, I would grow silver 2 barium 3, and then I'd have a eutectic solidification. I would have a mess. Incongruently melting materials are hard to grow by just solidifying a stoichiometric melt. Okay? Well, there are ways around that. Okay? Now, the final thing here, we won't probably have time to discuss this in detail today, but some phase diagrams have these compounds that instead of being a line compound, a well-defined stoichiometry, they have a width of formation. This is nominally silver 5 barium, but could have a little more silver, a little more barium. If you're an engineer, this might offer you the possibility of tuning the material. Okay? If you're a basic physicist, it means that you might have trouble reproducibly getting exactly the same material with exactly the same behavior, and that can be difficult. Okay? Now, having introduced you with how to read a binary phase diagram, let's now look at an example. Okay? Unfortunately, I wasn't able to bring a centrifuge and a furnace, whatever here, but I can at least show you pictures of how you actually grow something. Okay? So let's have an idea. We want to grow cerium diantimonide. Okay? It's sort of interesting. It's not quite a van der Waals solid, but it's a metallic micaceous. It foliates. It has interesting magnetic properties. Okay? So here is cerium antimony 2. It has, oh, by the way, these dotted lines mean that this is the best guess for the phase diagram that people had at the time. It means that measurements were done up to the solid lines, and this is sort of creative guessing. But within creative guessing then, cerium diantimonide decomposes somewhere in the 1400 C region, okay? And if we want to get to a homogeneous liquid, we need to be about above 1600. These are high temperatures, vapor pressure reactivity would be very difficult. On the other hand, I have this beautiful Liquidus line that will let me grow cerium diantimonide, reaching all the way down to relatively low temperatures. So this is an example of a material we can grow out of excess antimony. So we're going to grow cerium diantimony out of excess antimony. Okay? Nice. So what do? Well, we need to hold this in something. So I have these nice little cups. I call them crucibles. Everyone calls them crucibles. These are 2 ml. They fit over the tip of my pinky. Okay? I have those. I also take a silica tube and I seal off the bottom because I'm going to be having these crucibles inside this silica tube. Okay? This is a growth that has less than 12% rare earth. I probably can get away with using alumina crucibles. We'll talk about crucible choice a little later in the talk. I can pack my elements, my antimony and my cerium, into a crucible. I have a second crucible that I put a bunch of quartz wool, or in some cases I have a little filter here that will help me separate the liquid from the crystals once I'm done with the growth. I have my elements down here. I have my quartz wool up here. Okay? And now I'm going to take these to the glass bench. This is a hydrogen-oxygen torch. It's a very hot flame. I can put the tube in there. I can manipulate it. And I can put a hourglass-like neck here. So I can still pump through this, but it will be easy to seal. I hook this up to a pumping manifold. I pump it out. I flush. I pump flush. I backfill with a tiny bit of argon. And then I take the torch. I seal this off. And I now have my ampule. I have it in a larger crucible just so it stays upright in the furnace. Here's the furnace area. This can heat up to 1,500. For this growth, I only be going as high as 1,200. That's a little thermocouple in back to keep track of temperature. I program the temperature profile I want to, and I heat up. I go to a maximum temperature. I slowly cool down. Okay? And then I'm left with a sort of bifurcation, a decision. If I were growing salt crystals or sugar crystals out of water, and I really just was overly enthusiastic, and I cooled them down, cooled them down, cooled them down, and I cooled them down to -50 Celsius. I'd have my crystals, but I'd have solidified the water around them. And then I would have to take the ice and break the ice, and I crack the crystals, and I'm sad. Sort of stupid to cool down that low. Okay? Same thing here. I'm growing this out of excess antimony. If I cool it down to room temperature, I've solidified all the excess antimony around my crystals, and then I have to break them and hack them and do things. On the other hand, I can just pour off the liquid. The problem is antimony is a little bit viscous, okay? So if I were just to turn this upside down, if you're familiar with honey or molasses, it would be very slow dripping. It wouldn't be very efficient. On the other hand, I can have an accelerated process where I put them into a centrifuge and it spins and I get somewhere between 100 and 1000 G. The antimony just goes to the other side. Okay? So I end up with a crystal like this. This is a crystal of cerium diantimonide. Okay? If I were to look at just the lab book, it would be cerium diantimonide out of antimony. It was about 5% cerium, 95% antimony. I heated up to 1190, cooled down to 700, and then put it into the centrifuge. Okay? Now, this is a beautiful example of what geologists call a cryptomorphic material. Latin, crypto, hidden, morphic, shape, hidden shape. Look, circular is not a symmetry you get from any Bravais lattice. Okay? This is circular or elliptical because it grew to the limits of my crucible, which had a circular inner diameter. This is a happy crystal. This is one that's going to grow big and I can do lots of nice things with. Okay? Now, I wanted you to have a sense of how you make something like this. Okay? Now, having done that, let's look at another example. Okay? Here, we can switch. This is cobalt tin, pure cobalt and tin. Okay? This is a material, if I want to grow cobalt tin 1,1, this is something that decomposes paratectically, okay? If I were just to try to cool cobalt and tin, I would grow first this cobalt 3 tin 2, then cobalt tin, and then cobalt tin 2. Again, it would be sort of a mess. On the other hand, I can intersect this liquidus line for the primary solidification of cobalt tin, okay? So, now, when I gave this talk in Madrid, probably about 9 years ago now. I've given this talk several times. Poor Herman has seen this talk too many times. He's just a patient man. Okay? When I gave this talk, a number of years ago, I was accused of something very worrisome. Okay? I was accused of engaging in alchemy. Okay? And given that in Madrid there's a history of the Spanish Inquisition, and I know what they used to do to alchemists in the old days, I did not feel comfortable with this accusation. Okay? And the reason for this concern is, as we do this, it seems sort of miraculous because I'm starting with a cobalt 20 tin 80 solution, and at the end I have a solution that's almost pure tin. Sort of, am I changing cobalt into tin? So let's look carefully what's happening here, because it's actually sort of remarkable, and it bears some understanding. Okay? So let's look at points A, B, and C. Point A, I'm in this single phase region, okay? I'm just above this temperature of intersecting the liquidus line. I have a homogeneous liquid that's 80% tin. At point B, I've started growing some of this cobalt tin, okay? And the liquid is more concentrated in tin. And at point C, I've grown a lot of cobalt tin, and I have very little cobalt left in the liquid, okay? That's just sort of reading off these points. Now, that's nice, but I've basically just sort of read the composition of each of these points. I haven't given you the insight that you might actually need. Okay? So, let's look at another version of this. This I consider more useful. I literally have 80 blue blocks and 20 red blocks. So this is my cobalt tin mixture at high temperatures. Now, I'm at this temperature. It's a liquid. Okay? Now, as I start to cool down, I'm starting to grow cobalt tin, an equal number of these blocks, okay? Let's grow some more, grow some more, grow some more. As I grow more of this 50-50 crystal, I'm depleting the red blocks out of this solution, okay? What's happening is I'm growing a compound that has a much more cobalt-rich stoichiometry than my initial melt. Therefore, as I grow this 1,1 compound, I'm depleting the cobalt out of the melt. That's what's happening as I go down this liquidus line. Okay? That's the essence of solution growth. Okay? So, not alchemy, just old-fashioned chemistry, but for students of history of science, it's wonderful to see how chemistry and physics emerged from the old alchemical studies. And if you, during the question time, want to ask about the names of elements, if you look at some of the more archaic names of elements, there are beautiful alchemical, historical, mythical stories associated with them. Okay? So, time for some practice. So, here is alpha manganese bismuth. Okay, this is the bismuth manganese phase diagram. I originally was choosing this just as a perverse example. Subsequently, like with the cobalt tin, we ended up growing them and doing neat measurements on them. Okay? So, students of any age, but not from Madrid, how would you propose growing this compound? Single crystal form, out of a melt. As I explained to Herman, I grew up in a Quaker meeting. Silence does not bother me. So I will wait. We'll choose someone from the back row. You, sir. How would you suggest that we grow this compound out of solution?
Well, it would just split if we just reduce the temperature, so...
No, what composition? How do you suggest we grow this? What do I put in my crucible?
5% of manganese.
5% of manganese. Something here? Absolutely. So, in many cases, people say, oh, you want this, come in with a stoichiometry. Okay? This is a disaster because you'll grow various forms of manganese, you'll form beta, you'll do this because you're rolling down this liquidus line. Your answer is absolutely correct. I was pushing it more toward 8%, but basically you want to intersect this line below this paratectic decomposition. Then it works. Okay? So, other example. Aluminum 7, strontium 8, this material. Okay? Again, if we want this, here's the decomposition. Again, great numbers. This decomposes at 666 Celsius. It's as if we know where we are. Good. So this decomposes at 666. Basically, any composition here will give us aluminum 7, strontium 8. Okay? Now, let's return to the cerium antimony binary phase diagram though. Okay? The cerium antimony binary phase diagram has many compounds. We saw how we could grow cerium diantimonide, but for example, we might want to grow cerium monoantimonide. Okay? And since we're physicists here, or at least many of us are physicists, okay, we might ask the question of, why would you want to grow this? These just seem to be crazy compounds and names or whatever, so let me now show you a different type of phase diagram. The neat thing about creating materials is you end up being very multilingual in terms of phase diagrams. This is a metallurgist type of phase diagram, temperature, composition. Now let's go to a physicist type of phase diagram. Why would we want to grow cerium monoantimonide? Because the phase diagram, field versus temperature, is crazy. This is a material that has a devil's staircase. God, I have all these references here. Okay, so it has a devil's staircase of metamagnetic transitions or temperature-dependent transitions. As I cool this down in low field, I have 1, 2, 3, 4, 5, 6, 7, 8 phase transitions of different types of antiferromagnetism as I cool down. If I apply a field, I have an incredible cascade of steps of metamagnetic phase transitions. This is the compound that motivated Per Bach to have the anisotropic next nearest neighbor interaction model, the NE model, okay? It's also recently been considered a possible topological material, okay? There are a lot of reasons for wanting to grow this material, okay? So, physicists look at this phase diagram and go, wow. And if you want to make it, you then need to look at this phase diagram and figure out, how can I make it? Okay, so now, let's try to make this material because it's neat. Okay, this is congruently melting, so you can say, yeah, I just have a homogeneous liquid, I cool it down, I'm done. Except, this homogeneous liquid requires you to get around something like 1700, 1800, which is a really, really, really high temperature. The vapor pressure of antimony will be obscene, cerium will be rather nasty, the reactivity is hard, and let us not forget entropy. Okay, because the entropic disorder at that temperature is not small either. Now, Hülliger and Vogt at ETH Zurich did grow this in the 60s and 70s by a process they called mineralization. They basically took cerium and antimony, sealed it into a steel tube, put it into a furnace, ran away and covered their ears, and hoped it didn't explode. And they did get nice crystals, okay? But they did have a degree of disorder. Now, you can do it that way, but it's not the easiest way, okay? There are other ways of doing this. I keep losing this button. Here we go. So, we could try to use solution growth, okay? Now, we could try to grow it